Welcome to MSP lecture series on main group chemistry. In my last lecture, I initiated discussion on organometallic chemistry of main group elements, and while discussing the synthetic methodologies that are available for the preparation of organometallic compounds, I did mention about metathesis and transmetallation reaction or reaction of metal with halide sources. So, let me continue from where I had stopped. This metathesis reaction involving the same central element are often referred to as redistribution reactions. For example, SiCl4 when it is treated with tetramethylsilane, so redistribution occurs to give a mixture of products such as Me3SiCl plus Me2SiCl2 etc. Okay. So, this is called redistribution reaction. Similarly, treatment of germanium tetrachloride with trimethyl aluminum it gives trimethyl germanium plus tetramethyl germanium plus 4AlCl3. Okay. So, aluminum is more electropositive than germanium. So, this reaction occurs as it is thermodynamically favorable, because here the stability of trichloroaluminum is much more stable compared to trimethyl aluminum, because trimethyl aluminum is more electro deficient, whereas aluminum trichloride is not really electron deficient, but it forms a dimer utilizing the chlorine lone pair. So, here despite aluminum having more electropositive than germanium, this reaction occurs as it is thermodynamically favorable. So, now let us look into another method or route called hydrometallation. Okay. So, the reaction is driven by the high strength of EC bond relative to that of most EH bonds, and occurs with a wide variety of compounds that contain EH bonds. Well, E is a main group element. For example, you can see hydroboration reaction I have shown here. If you take this ether adduct of boron trihydride, treat with alkene in ether. So, hydroboration occurs through the elimination of Or2. Similarly, one can also perform this hydrosilylation reaction, but this requires a catalyst, preferably a transmetallic catalyst such as platinic acid here H2PtCl6. This reaction is carried out in 2-propanol, and here SiH bond is added across this carbon-carbon double bond. So, this is called hydrosilylation reaction. The slight differences that arises between organometallic compounds and binary hydrogen compounds is mainly due to the tendency of alkyl groups to avoid ionic bonding. For example, the molecular structure of trimethyl aluminum and methyl lithium differ from aluminum trihydride and lithium hydride. Even the more ionic methyl potassium crystallizes in the nickel arsenide structure rather than rock salt structure adopted by KCl. So, that means nickel arsenide structure is typical of soft cation soft anion combination. So, electron deficient compounds such as trimethyl aluminum contain 3 center 2 electron bonds similar to BHP bond we come across in case of diborane. So, you can see here nickel arsenide structure, okay, and of course, in the lattice this is how the arrangement of nickel and arsenide anions are shown here. The local coordination of cation around the anion is shown in this one. The first one, there are 6 nickel arranged in a trigonal prism around this central arsenic. Arsenic is central here, and here in case of nickel A6, here the local coordination of anion around the cation is shown here. It is octahedrally surrounded by 6 arsenide ions. So, both are hexacoordinated. Okay, so let's look into the structure of methyl lithium. Methyl lithium in nonpolar solvents consists of a tetrahedron of lithium atoms with each face bridged by methyl group. So that means in a simple way one can write, although this is referred to as a Cuban structure having alternate corners occupied by methyl and lithium. Let me just consider a tetrahedron of lithium atoms here. So now we have 4 equilateral triangle faces consists of 3 lithium atoms. So here essentially if you assume in case of CH3 fragment we have here, carbon has undergone sp3 hybridization having 4 sp3 with 1 electron each, here something like this, and having here H, and now we have 1 with 1 electron is there, and out of this one 1 electron will be available. So essentially this one comes here and sits here in one of the faces. So something like this can each face, something like this, and here so and here. So something like this. This eventually gives a tetrahedral structure. That is what I have shown here. Here you can see here, and of course this can also be simply shown in this fashion. And if I put here, so you can see here now 3 are there and this one is coming, and of course one can show in this fashion. Your sp3 is coming here. Okay, so another 2 lithium atoms will be flanking from the other position. This is how exactly it shows here. So you have methyl group. Okay, so this gives some idea about essentially it shows having 4 centered 2 electron bonds. Each lithium has 1 electron and each methyl group has 1 electron, so that we have essentially 4 electrons from methyl groups and 4 electrons from lithium, that forms a covalent bond, and remaining lithium atoms are not contributing anything. As a result, what we have is 4 centered, 3 lithium and 1 carbon constitute 4 centered, but we have 2 electrons. So here we have 4 centered 2 electron bond. Okay, so you can see that one, and of course one can also write in this way. This is bonding orbital and these 2 are non-bonding orbital and this is anti-bonding orbital. So through MO diagram also one can represent. This involves 3 lithium 2s1 orbitals and 1 sp3. So here we have 4 orbitals essentially that constitute 1 bonding orbital where these 2 electrons reside, and we have 2 non-bonding and 1 anti-bonding. So this is how one can explain the bonding in methyl lithium. Okay. So the lower energy of the carbon orbital compared with the lithium orbital indicates that the bonding pair of electrons will be associated primarily with the CH3 group, thus supporting the carbon ion character of the molecule. Since the carbon is much more electronegative, the shared electron essentially resides on carbon, making it more electronegative. So that means that is increasing its carbon ion character. As a result, what happens? This is much more reactive. Okay. Similarly, dimethyl beryllium and dimethyl magnesium exist in polymeric structure with the 3 centered 2 electron bonding. That means CH3 bridges between each metal atom, that already I showed you in my previous lecture. Okay. So the group 12 metals form linear molecular compounds such as dimethyl zinc, dimethyl cadmium and dimethyl mercury that are not associated in solid, liquid or gaseous state or in hydrocarbon solutions. So they form 2 centered 2 electron bonds. Unlike beryllium and magnesium analogues, they do not complete their valence shells by association through alkyl bridges, the bonding in these molecules are very similar to D10 metals such as copper 1, silver 1 and gold 1 having linear geometry. Okay. This tendency is sometimes rationalized by invoking PD hybridization in M plus ion, which leads to orbitals that favor linear attachment of ligands similar to SPD hybridization. So, this is something unusual. Usually when two orbitals are mixed, it gives two hybrid orbitals, whereas here three orbitals are mixing to give two hybrid orbitals. So, something like this. The preference for the linear coordination may be due to the similarity in the energy of the outer ns, np and n-1 d orbitals, which permits the formation of collinear SPD hybrids. I am going to show you how this SPD hybrid orbitals look like. So, this is how it looks like here. This is dz square and this is s and this is pz orbital. Okay. So, they combine together to form two SPD hybrid orbitals. Okay. So, that means here the hybridization of S, Pz and dz square with the choice of phases shown here produces a pair of collinear orbitals that can be used to form strong sigma bonds. Now, these two SPD hybrid orbitals combine with carbon sp3 having one electron to form linear compound like dimethyl mercury or dimethyl zinc or dimethyl cadmium. Okay. Let us look into the reaction patterns. The reactions of organometallic compounds of electropositive elements are essentially dominated by factors such as the carbon ion character of the organic moiety and the availability of a coordination site on the central metal atom. So, carbon present on most electropositive metals are essentially very reactive reagents. So, let us look into these reactivity patterns by considering oxidation first. All organometallic compounds are potentially reducing agents. Those of electropositive elements are in fact very strong reducing agents and many of them are highly pyrophoric in nature. The strong reducing character also presents a potential explosion hazard if the compounds are mixed with larger amount of oxidizing agents. One has to be very careful and one should understand the nature of the reagents that are used in such reactions, so that any such explosion or any unwanted occidental reactions can be avoided. So, why these compounds are very reactive? All organometallic compounds of the electropositive metals that have unfilled valence orbitals or that readily dissociate into fragments with unfilled orbitals are pyrophoric. So, that is the reason most of these organometallic compounds, if we consider, they have unfilled valence orbitals or they have a tendency to dissociate into fragments with unfilled orbitals. As a result, they become highly pyrophoric in nature. So, let us consider these examples. Methyl lithium, okay, so Li4, Me4 or zinc, dimethyl zinc or trimethyl boron or Al2CH3 6 times trimethyl aluminum. So, they are all volatile pyrophoric compounds. For example, BCH3 thrice dimethyl boron may be handled in vacuum line and inert atmosphere techniques are used for less volatile but air sensitive compounds. Compounds such as tetramethyl silicon and tetramethyl tin, which do not have low lying empty orbitals, and if you consider silicon and tin, their 3D and 5D orbitals are very high in energy. So, as a result, what happens, they cannot really increase their coordination number from 4 to 5 or 6. As a result, what happens at room temperature, they do not react readily, they require elevated temperature to initiate combustion so that they can be handled in air. The combustion of many organometallic compounds takes place by a radical chain mechanism. So, let us look into the nucleophilic character of some of these reagents. The partial negative charge of an organic group attach it to an electropositive metal makes it a strong nucleophile and Lewis base. So, this is referred to as carbon anion character even though compound itself is not ionic. That means alkyl lithium and alkyl aluminum compounds and also Grignard reagents are the most common carbon anion reagents in laboratory scale synthetic chemistry. The carbon anion character diminishes for the less metallic boron and silicon, and the carbon anion character finds many synthetic applications. Okay, let me write some of those things for you. Let us consider lithium, alkyl lithium or Grignard reagents. Their applications are essentially similar. For example, if it is treated with O2, that means oxidation, that leads to the formation of ROH. Okay. And if it is treated with HX, okay, it leads to the formation of RH, so that LiX will come out. And if it is treated with water, hydrolysis, so it gives again RH. And treatment of this one with sulfuryl chloride, SO2Cl2, leads to the formation of R2SO2. Similarly, treatment of RLI or RMGX with thionyl chloride leads to R2SO. Okay. And if we treat this one with appropriate reagent EXN, okay, one can get ERN. Here E can be boron, silicon, germanium, tin, Pb or arsenic, antimony or even phosphorus. Okay. Of course, X is a typical halide. Okay. So, what would happen if you treat this one with a aldehyde and water followed by addition of water. So, with aldehyde and water it gives R2CHOH. Okay. If you take a ketone and water, it gives tertiary alcohol. So, these are some of the reactions. These are all very important reactions in organic synthesis to generate a variety of useful compounds. And of course, these two reactions are essentially called as metathesis reactions. These two reactions are essentially called as metathesis reactions. And this is oxidation reaction, this is hydrolysis reaction, and one can use several other reactions and they come very handy in synthetic organic chemistry and also in inorganic chemistry. So, I have shown here the same slide here, you can just see its use. Let us continue the reactivity patterns of some of these organometallic reagents. For example, trimethyl aluminum, when it is treated with ethanol, it forms triethoxy aluminum through the elimination of 6 equivalents of methane. So, how that happens is shown here. Since here this dimer breaks, as a result one coordination site is vacant, that is occupied by oxygen lone pair, and then this H moves towards this one in the slow step to form dimethyl aluminum ethoxide through the formation of CH4. This continues with, if another equivalent of ethanol comes, eventually it replaces OET, ethoxide groups replace all methyl groups and they come out as methane. So, Another one is Lewis acidic nature of organometallic compounds. Due to the presence of unoccupied orbitals on the metal atom, electron deficient organometallic compounds are observed to be Lewis acidic in nature, or they perform as Lewis acids. So, let us look into the Lewis acidity of these compounds. For example, if I take triphenyl boron, if it is treated with phenyl lithium, it forms lithium tetraphenyl borate. Okay. So, this reaction may be viewed as the transfer of the strong phenyl from the weak Lewis acid to the weak Lewis acid is lithium plus to the stronger acid B3. So, that means migration of pH minus or C6H5 minus from the weak Lewis acid, that is Li, plus to the stronger Lewis acid B3. Okay. So, that means there is always some driving force for this kind of reactions. Organometallic species that are bridged by organic groups can also serve as Lewis acids, and in this process bridge cleavage can take place readily. For example, I have shown here trimethyl aluminum is a dimeric compound, something like this. So, bridge breakage takes place across, and if here addition of two equivalents of triethylamine, say, it leads to the formation of two so this is how adduct is formed here. So, electron deficient organometallic species are essentially perform as Lewis acids. Now, let us look into the ionic and electron deficient compounds of group 1, 2 as well as group 12. So, organometallic derivatives of all group 1 metals are known. Amongst the alkyl lithium compounds are most thoroughly studied and useful reagents. Many of them are commercially available. So, N-butyl lithium, phenyl lithium, tertiary lithium, all those things in different concentrations in mostly in hexane or pentane, 1 molar solution, 1.6 molar solution or 2.5 molar solution in 100 ml or 500 ml or in 1000 ml containers. So, methyl lithium is generally handled in ether solution, but Li compounds with longer chain are soluble in hydrocarbons. So, commercial preparation, as I mentioned, it can also involve M plus Rx gives Mr. Okay. They are often contaminated with halides. In this method, basically what happens, we are taking two equivalents of M and Mr and Mx comes. This is the commercial method of preparation of methyl lithium or ethyl lithium or tertiary lithium. But the best method for the preparation of these compounds which are free from contaminated halide is to go for transmetallation method. For example, dimethyl mercury or dialkyl mercury, when it is treated with two equivalents of lithium, it gives 2 LiR and mercury comes out. Okay, so, this is the best method. Of course, one also should be careful about the contamination of these compounds with mercury. Methyl lithium exists as a tetrahedral cluster in the solid state and in solution, that is already clear. Many of its higher homologues exist in solution as hexamers or equilibrium mixtures of aggregates ranging up to hexamers. The larger aggregates can be broken down by Lewis bases such as TMEDA, that is tetramethyl diamine. You can see here it can also exist in hexameric form, something like this here. We have 6 lithium atoms are there and 6 alkyl groups are there. So, common organolithium compounds have normally 1 lithium per organic group like methyl lithium, phenyl lithium, N-butyl lithium, tertiary butyl lithium, secondary butyl lithium, like that. But several polylithiated organomolecules containing several lithium atoms per molecule are also known. The simplest example is Li2CH2, which can be prepared by the pyrolysis of methyl lithium, which crystallizes in a distorted antifluoride structure. However, the finer details of the orientation of CH2 groups are yet to be established because of its high reactivity and less stability. Here, in case of phenyl lithium, okay, one can see here this is how the structure looks like. Here is phenyl lithium with tetramethyl ethylene diamine, it forms a dimer, and of course, here it is getting stabilized because it utilizes this pi electrons of benzene to stabilize or overcome some of the electron deficiency of lithium here. Okay, and this is the structure for Li2CH2, similar to fluoride structure, that is calcium fluoride structure. Sodium naphthalide is an example of an organometallic salt with a delocalized radical anion C10H8-. Such compounds are readily prepared by reacting an aromatic compound with an alkali metal in a polar aprotic solvent. Usually tetrahydrofuran is used. So, naphthalene dissolved in tetrahydrofuran reacts with sodium metal to produce a dark green solution of sodium naphthalide. So, that means you can see here sodium solid when it is added to naphthalene in THF, it forms this sodium naphthalide. This dissolves in solution and which is green in color. So, EPR spectrum shows that the odd electron is delocalized in an antibonding orbital of C10H8. So, formation of radical anion is more favorable when the pi star of lowest unoccupied molecular orbital of the arene is low in energy. So, simple molecular orbital theory predicts that the energy of LUMO, lowest unoccupied molecular orbital, decreases steadily on going from benzene to more extensively conjugated hydrocarbons. As a result, they have a tendency to form some of these kind of stable sodium salts, which come very handy in organic synthesis. So, why sodium naphthalide is very important in organic synthesis is sodium naphthalide and similar compounds are highly reactive reducing agents. So, they are preferred to sodium metal because unlike sodium they are readily soluble in ether. Another problem is weighing accurate amount of sodium is very difficult because on even slightest exposure the surface will be coated with sodium oxide and we lose a certain quantity of sodium. So, in this case what happens when the stoichiometry of the sodium salt is very critical, then using sodium metal is not a good idea. So, instead one can use sodium naphthalide where exact quantity of sodium can be taken in solution by finding out the molarity of the sodium naphthalide solution and taking the right amount of sodium naphthalide. So, the resulting homogeneous reaction is generally faster and easier to control than a heterogeneous reaction between one reagent in solution and pieces of sodium metal, which are often coated with unreactive sodium oxide or with insoluble reaction products. In this context, the utility of sodium naphthalide comes into the picture in organic synthesis, where the stoichiometry is very critical. The additional advantage is that by proper choice of the aromatic group, the reduction potential of the reagent can be chosen to match the requirement of a particular synthetic task. So, that means whether one has to carry out under mild condition or an ambient condition, by knowing that one can choose a right kind of aromatic group so that its reduction potential can be match the requirement of a particular synthetic scheme that is planned. So, alternate route to delocalize the anion is the reductive cleavage of acidic CH bonds by an alkali metal or alkyl metallic compound. Okay. So, here you can see here. So, in butyl lithium is treated with 4 equivalents of TMEDA. In presence of naphthalide, it forms a compound of this type. Okay. So, one can also conveniently use this one as a source of lithium. And sodium and potassium also form intensely colored salts with many aromatic compounds. In reactions such as this that I showed you, the oxidation of the alkali metal involves the transfer of one electron to the aromatic system, producing a paramagnetic radical anion. So, let me stop here and continue in my next class the remaining organometallic chemistry of main group elements. Thank you very much.